We have seen the introduction of magnetic field. Magnetic field is property of the space where a charge which is under motion experience a force. Now we want that what is meant by intensity of magnetic field, because in physics everything is measured. The measurement is the essence of the physics. So this magnetic field we are trying to define. We also want the measurement of its intensity. Is it that magnetic field at certain location is very strong, at the other location it is mild? If it is so, then can we measure it? If we can, then how we can measure it? Okay, I give you one example, that if a charge placed here and now we move it and I move it, it goes straight. Okay, I take it to another place and move it again with the same velocity. Now what I find, that it goes like this and it bends this way. Normally when I push it in this direction, it should go straight according to the rules of inertia of velocity, but here it goes like this. I take it to room number 2 or room number 3. In that I find that now if I give it a velocity, then it goes like this. So in place of going straight, it has bent like this. All these things, by our knowledge of mechanics, we understand that there is a force acting on this charge, force. And because of this force, this charge bends like this. So there is a force acting on it. Now what is the difference in room number 1, 2, 3? We have created magnetic field in room number 1, in 2 and 3, and now I am in a position to say that in room number 1 there is no magnetic field. In room number 2 there is a magnetic field. In room number 3 there is a magnetic field B3, and here the force is 0. Here force, I should say, F2, and here force is F3, and it is very clear to you now that this force is largest of F3, F2 and F1. Okay, so this gives me indication that larger is the force, larger will be bending from its path, and this makes a circle, large circle, this makes another circle, this makes another circle. So curvature goes on increasing. So that means more force is there. Okay. Now why this force is increasing? We have no other reason, because we are using same Q in all the 3 cases, same velocity in all the 3 cases. Then what has changed? In all the 3 rooms we have different magnetic field. So here we will say the intensity of magnetic field is changing. Now in the previous lesson we have done it. This force depends upon so many things, and I would like to mention that in all which quantities the force is acting upon. I take another example. There is a magnetic field in a room. Here I send a charge Q1, it goes like this. I send a charge Q2 with the same velocity and it goes like this. I send a charge Q3 and it goes like this. Which is experiencing more force? Answer: Q3 is experiencing more force. Velocity is same, room is same. What does this mean? This means this force is proportionate to charge. Here what I have done, that Q3 I have taken which is larger than Q2 and it is larger than Q1. More is the charge, more is the force. Okay, here more is the magnetic field, more is the force. The third thing now I apply, and that is with velocity. If I give it a certain velocity, change the velocity, Now I find the curvature goes on decreasing. Here velocity is v1, v2, v3, and what is the relation? v3 is larger than v2 is larger than v1. So curvature is more in case of v3. Right. Now Q is same in all the three cases and they are in the same room, so B is same. Now I find if I increase Q, the force increase. Force. If I change velocity, the force increase. If I change magnetic field, the force increase. So F is proportionate to Q, F is proportionate to V, and F is proportionate to B. Combining all the three, I get F is proportionate to Q, V, B. Here. So in this, there should be a constant. F is equal to K, Q, V, B. But this constant, we can make it 1 because in this topic, B has been introduced as a new quantity for the first time. Whenever we introduce a new quantity for the first time, we have an advantage that we define it in such a way that K become 1. Then how we will define it? Here B is equal to F upon Q V, and there is a constant here, either here, anywhere you place, doesn't matter, this constant. Now if I ask you that the unit of B is chosen in such a way that if the charge is 1 coulomb, velocity is 1 meter per second, then force is 1 unit, 1 Newton. Then I will take B as 1 unit. Then this formula, in this case, K will become equal to 1. So I will write it here. If F is equal to 1, Q is equal to 1, V is equal to 1, and then we take or define B as 1. F is equal to 1 Newton, Q is equal to 1, velocity is equal to 1 meter per second, then B will be taken as 1. This will be definition of B, we will do in the next lecture, but here if B is equal, we define B is equal to 1, then K is equal to 1. Put everything 1 there, K will be 1, then F is equal to Q, V, B. This. So we have a relation, force is equal to QVB. Okay. Now with this relation we make B is equal to F upon QV. B is equal to F upon QV. Now I want to define B with help of this. How do I define with help of this? B is equal to F if Q is 1 and V is 1. This gives me a definition. What is the definition? If 1 coulomb charge is moving with velocity 1 meter per second, then whatever is the force experienced on the charge is strength of magnetic field at that point, at that location. So I will write it for you. In F is equal to QVB, B is equal to F. And this gives us the intensity of magnetic field definition. I will write it. This formula, please see, F is equal to QVB. This is actually FQV cross B. If we write the complete details of it, this will be F is equal to QVB sine theta. Now, what is this theta? Theta is the angle between velocity and magnetic field. If at any place this is the direction of magnetic field, this is direction of velocity, then it matters whether they are at right angle or they are parallel. We have observed if they are parallel, there is no force. If they have an angle between them as 90 degree, B is here and the charge is travelling here, then it experiences maximum force to turn this way. But if B and V are in the same direction, there is absolutely no force here. That is why this figure sin theta is there. If theta is 0, no force. If theta is 90, maximum force. That is why in our definition we have written right angle, so that sin theta has also become equal to 1. Now you see in this, moving at right angle, there is intensity of magnetic field at any location is the force experienced by this unit charge. This makes Q equal to 1. Right angle, this makes sin theta is equal to 1 to the field with unit velocity. Unit velocity make V is equal to 1. This makes sin theta is equal to 1, and this unit charge, this makes Q is equal to 1. So if this 1, 1, 1 is made, then what do we get? B is equal to F. So intensity of magnetic field at any location is the force. So this is definition of magnetic field at any location. Now there is direction of the magnetic field. Direction of the magnetic field is always given by left hand rule. With left hand rule, the first thing, these three fingers, this we will call thumb, this is index finger and this is middle finger. These three we have to keep as right angle to each other, making it X, Y and Z direction. Okay, this and this can be rotated anyway, but the angle between them will always remain 90 degree. Now place this along B, that is given to us. Now if I have placed it along B in this direction, I have a freedom to rotate this. This will remain in this direction. So this will represent magnetic field direction. If my charge is moving in this direction, this finger is showing the velocity of charge. If the charge is going up, then I will rotate it this way. If the charge is going this way, then I will rotate it this way. If the charge is going down, I will rotate it this way. So I am free to rotate it. Keeping B in the same direction, I can rotate it. So if this represents B, this I will rotate in the direction of velocity of the charge. Set. Now these two things are set. This will give me the information in which direction will be the force on the charged particle. So if the charge is going down, it is the force is in this direction and the charge will move like this. Force in this direction. Okay. Now if B is here and the charge is going in this direction, I will put it this way. This is the force and the charge will go up. Okay, if the charge is going in that direction, this is B, this is direction of the charge, down. So the charge will go like this, turn down. If the B is upward, I will keep the B upward. The charge is going this direction, the charge moves like this. This is the force. This says that when the charge is going like this, it will bend this way, in this direction. So this gives the direction of force and it will turn towards that direction. So this is left hand rule. This gives us direction of force and the direction of turning. So this is known as turning direction is given by left hand rule, or we can say force direction. Force direction or turning direction. So this is quantity of the force. This is turning direction of the force. Formula for B, F upon QV. Because K have made as 1. So this is what we have studied in this lecture. In next lecture we will see what is meant by 1 unit magnetic field.